Welcome to G Fun Facts Online. Today we are looking up, past the clouds, to the very edge of the world. We are talking about the atmosphere. It is the thin, fragile veil that separates biology from the void. It is the difference between the barren, cratered wasteland of the moon and the lush, breathing biosphere of Earth. But we often make the mistake of thinking atmospheres are permanent fixtures. They are not. They are fugitive things, constantly seeking to escape the gravitational clutches of their parent worlds. For decades, planetary scientists held a simple, intuitive belief. They thought that a strong magnetic field was the essential shield that protects a planet's atmosphere from the ravaging winds of its star. It was the standard explanation for why Earth thrived while Mars withered. But recent discoveries, from the peaks of Earth's polar fountains to the desolate plains of Mars and the crushing depths of Venus, have complicated this story. We are now learning that magnetospheres are not just shields. They can also be funnels, traps, and engines of loss. This is the story of the invisible war between gravity and radiation, the mechanisms of atmospheric escape, and the complex, often misunderstood role of magnetic fields in the survival of worlds. To understand how a planet dies, we must first understand how an atmosphere lives. An atmosphere is essentially gas held down by gravity. But gas is not static. It is a chaotic swarm of particles, each vibrating with thermal energy. If a particle moves fast enough, surpassing the escape velocity of the planet, and does not hit another particle on its way out, it leaves forever. This brings us to the first mechanism of loss, known as thermal escape, or Jeans escape, named after Sir James Jeans. Imagine the atmosphere as a bell curve of particle speeds. Most particles move at an average speed determined by the temperature. But the tail of this curve contains outliers, particles moving significantly faster than the average. In the upper reaches of an atmosphere, at a layer called the exobase, the air becomes so thin that collisions stop. If a lightweight atom, like hydrogen, happens to be in that high-velocity tail and is moving upward, it simply floats away into space. This is the mass factor. It is why Earth has lost almost all its free hydrogen and helium. They are light, fast-moving, and easily reach Earth's escape velocity of 11.2 kilometers per second. Heavier molecules like oxygen and nitrogen are generally too sluggish to escape via this method on Earth. However, in a planet's violently hot youth, or for planets too close to their stars, the upper atmosphere can heat up so much that it expands explosively. This is called hydrodynamic escape. In this scenario, the atmosphere does not just leak, it flows. This planetary wind can drag heavier elements like carbon or neon out into space along with the hydrogen, a process believed to have sculpted the early atmospheres of Venus and Earth. While thermal escape is a slow, gentle leak, for many planets, the real danger comes from violence. These are the non-thermal escape mechanisms. These involve external forces, usually the host star, imparting massive energy to individual atoms, kicking them out of the gravity well. One such method is photochemical escape. Ultraviolet light from the sun strikes a molecule, like oxygen or carbon dioxide, in the upper atmosphere, breaking it apart. The energy of the chemical bond snapping releases heat, flinging the resulting atoms apart at high speeds. If one is aimed upward, it escapes. Then, there is sputtering. Think of this as a game of cosmic billiards. High-energy ions from the solar wind slam into the atmosphere, crashing into neutral atoms. These collisions scatter particles in all directions. Some are knocked backward into space. This mechanism is brutally effective on worlds without magnetic fields to deflect the incoming wind. There is also charge exchange, where a fast-moving solar wind ion steals an electron from a slow-moving atmospheric neutral atom. The solar ion becomes a fast-moving neutral that is no longer affected by magnetic fields and continues its trajectory, often crashing into the atmosphere or escaping entirely. The atmospheric atom becomes an ion, suddenly vulnerable to electric and magnetic forces. This brings us to the great debate of modern planetary science. Is a magnetosphere a shield or a funnel? For a long time, the consensus was that Earth's intrinsic magnetic field acts as a force field. The solar wind, a stream of charged protons and electrons moving at 400 kilometers per second, carries its own magnetic field. When it hits Earth, it is deflected around our planet, forming a bow shock. The atmosphere inside is safe from the direct stripping force of the wind. Mars, lacking this dynamo, was supposedly stripped bare. However, recent studies, including those by Gunnell and colleagues in 2018, and data from the European Space Agency's cluster mission, have suggested a startling counter-narrative. A magnetic field makes a planet look bigger to the solar wind. While it blocks direct stripping, it connects the planet to the solar wind's energy through magnetic field lines. Specifically, we must look at the polar cusps. Earth's magnetic field lines funnel vertically into the north and south poles. These are open wounds in the shield. Solar energy pours down these funnels, heating the ionosphere. This heating causes ions like hydrogen, helium, and even oxygen to flow upward along the field lines. Instead of being trapped, they are guided out into the magnetotail and stripped away. This is the polar wind. The verdict implies that a magnetosphere shields a planet from sputtering, but it facilitates polar wind escape. The net result is shocking. Earth loses atmospheric ions at a rate of roughly 1 kilogram per second. This is surprisingly similar to the loss rates of unmagnetized Mars and Venus. The shield might actually be a sieve that simply selects different elements to lose. Let us look at the case studies in our own solar system to see how this plays out, starting with Mars, the dying world. Mars is the tragic protagonist of atmospheric science. 4 billion years ago, it had a thick atmosphere and liquid oceans. Then, its internal dynamo died, and the magnetic field collapsed. NASA's MAVEN mission arrived in 2014 to solve this cold case. It confirmed that the solar wind was indeed the murderer. MAVEN measured that 65% of Mars' argon, a heavy inert gas, had been lost to space. Since argon does not react chemically, it can only be removed by physical sputtering. This confirmed that the vast majority of Mars' air was physically knocked into space by the Sun. Furthermore, Mars currently loses hydrogen at a seasonal rate. When Mars is closest to the Sun and dust storms heat the lower atmosphere, water vapor rises high, gets broken by UV light, and the hydrogen escapes. Mars is essentially bleeding its remaining water into space. Next, consider Venus, the heavy survivor. Venus is an enigma. It has no intrinsic magnetic field, yet it possesses an atmosphere 90 times denser than Earth's. If magnetic fields are essential shields, why is Venus so thick? The answer lies in the induced magnetosphere. Although Venus generates no field, its ionosphere is so thick that it conducts electricity. When the solar wind hits Venus, it induces currents that create a draped magnetic field. This induced magnetosphere is surprisingly effective at deflecting the solar wind around the planet. However, Venus did lose something important: its water. ESA's Venus Express discovered a massive electric potential drop in Venus' upper atmosphere, known as the electric wind. It is strong enough to strip heavy oxygen ions. Venus kept its heavy carbon dioxide thanks to gravity, but the electric wind stripped the lighter hydrogen and oxygen that once made up its oceans. Finally, we have Earth, the leaking blue marble. We are the control group. We have a strong dipole field. We retain our water and nitrogen, but we are not sealed tight. In the 1980s and 90s, spacecraft imaged a fountain of plasma erupting from Earth's poles. We are constantly spraying oxygen and hydrogen into our magnetotail. Some of this returns to Earth during magnetic storms, causing auroras, but much is lost down the tail, forming a cometary wake behind our planet. This explains the helium paradox. For years, scientists were puzzled why Earth's helium levels remain constant, despite continuous production from radioactive decay in rocks. The answer was the polar wind. Earth's magnetic field funnels helium out at the exact rate it is produced, maintaining a perfect equilibrium. As we look beyond our solar system, the question of atmospheric escape becomes a key to finding alien life. To categorize the thousands of exoplanets we have discovered, scientists Kevin Zonley and David Catling proposed the concept of the cosmic shoreline. Imagine a graph. On one axis is insolation, or how much light the planet gets. On the other is escape velocity, or how strong the gravity is. Below the shoreline are planets that are too hot and too small. Their atmospheres boil away. These are the barren rocks, the supermercuries. Above the shoreline are planets that are cool enough or massive enough to hold their gas. These are the habitable worlds and the gas giants. The shoreline is the empirical dividing line, where escape velocity equals roughly 4 to 5 times the thermal velocity of the gas. It neatly separates the Earths from the Marses and the Mercuries. However, there is a trap. The most common stars in the galaxy are red dwarfs or M dwarfs. They are dim, meaning habitable planets must orbit very close, often closer than Mercury is to the Sun. The threat here is that M dwarfs are violent. They flare with UV and X-ray intensity hundreds of times stronger than our Sun. A planet in the habitable zone of an M dwarf faces an X-ray wind that can strip an Earth-like atmosphere in less than 100 million years. Here, a magnetic field might be crucial, not just to stop sputtering, but to prevent the atmosphere from being eroded by the intense coronal mass ejections that strike these close-in worlds daily. We are seeing this now with the TRAPPIST-1 system. Preliminary data suggests the inner planets may be bare rocks, victims of atmospheric escape. So, is a magnetic field necessary for life? This is the billion-dollar question. The argument against it points to Venus, which has a thick atmosphere without a field, and Earth, which loses atmosphere because of its field. Perhaps gravity is the only thing that truly matters. If a planet is massive enough, it can afford to lose some air and still be habitable. However, the argument for the magnetic field suggests that we only see the current state of the solar system. In the early days, the Sun was 100 times more active. Without Earth's magnetic field during that violent epoch, our atmosphere might have been sputtered away before life could begin. A magnetic field might be a necessary umbrella for the planet's infancy, even if it becomes less critical in adulthood. This also impacts our dreams of terraforming Mars. If we were to melt its ice caps to release carbon dioxide, would it just escape again? Current science says, not immediately. Mars loses atmosphere at a rate of about 100 grams per second today. Even if we built a thick, Earth-like atmosphere, it would take roughly 100 million years for the solar wind to strip it back down to current levels. On human timescales, atmospheric escape is negligible. We do not need to build a magnetic shield to terraform Mars. We just need to fill the bathtub faster than the slow leak can drain it. Atmospheric escape is the sculpting hand of the cosmos. It determined why Mars turned red and rusty. It determined why Venus is a hellscape. And it maintains Earth's balance. We exist in a moment of equilibrium. Our gravity is strong enough, our magnetic field is complex enough, and our distance from the Sun is safe enough. But looking at the plasma fountain rising from the Arctic tonight, we are reminded that our atmosphere is not a cage. It is a river, slowly flowing into the sea of stars. We are not just living on a planet, we are living in the breath of a geologically alive world, protected by the invisible geometry of magnetism, fighting a 4 billion-year war against the vacuum. Thank you for listening to G Fun Facts Online.